My name real quick is Craig Lytle. I'm a CEO and founder of a company called AmperView, which is using artificial intelligence, machine learning, DNN algorithms in the area of youth sports. Having a lot of fun with that. But today we're covering different stuff today, and this next presentation is, again, as we look at the future of autonomous vehicles, one of the most basic things I want to make sure the vehicle does is not hit something else. That sounds super simple and super basic, but of course it's not. And our next speaker is going to talk about that in more detail. So Gergely Debreczeni, close, sorry about that. He's the chief scientist at AImotive, and he's going to talk to us about distance estimation and the various approaches to doing that in the autonomous driving space and ADAS more urgently or more short term. Come on up.
Thank you very much. I'm Gergely from AImotive. It's an honor to have the opportunity to speak here. I have been asked to give you a presentation which is slightly technical, give specific information, not just generated, and still can be followed by anyone who is interested. And we are not going to discuss deep technical details, but I really wanted to give you a topic which is simple but important enough to be presented. As mentioned, in ADAS and automated driving, distance estimation is really one of the basic, most important stuff. It's interesting because it's really simple in complexity, but it's very high. Its importance is very high. As mentioned, automated driving has many purposes. There are no such things as self-driving car. There are many different use cases, many different operation domains, many different requirements, safety levels. And all these kind of different solutions and business use cases using different sensor setup, different operation conditions, etc. What I want to say with this is there is no single golden solution. No, not for perception, not for decision making, and not for distance estimation. What I'm going to present now to you is a kind of toolkit that anyone can use to build up a distance estimation method suitable and safe enough, precise and robust enough for a specific use case. ADAS and AD shares a lot of common development philosophy, but they are also fundamentally different. Just give you an example. For example, in ADAS, if you have an ACC function guarantees that the car won't brake if there is nothing in front of the car. If there is empty space in front of the car, then the car should not brake, because otherwise the driving experience would be very bad. But an ADAS function, an ADAS ACC function, does not guarantee that the car will always brake. That's a very, very, very big difference compared to automated driving. In automated driving, you have to guarantee at an ACLD level to see objects and to guarantee an ACLD level to see the empty space, so not to brake when there is nothing in front of you. A distance estimation method, it's not only characterized by its precision, but of course its costs, its computational cost, its robustness, its operation domain usability. So it's really a multi-dimensional problem and must be designed along in the knowledge of the complete system. So we cannot really speak about separately. And the whole purpose of automation is really to replace the human and not to replicate it. Sometimes there are discussions, interesting discussions and interesting developments that try to mimic the human behavior and try to copy, to replicate the human behavior, which is, at one part, is very interesting because we can learn definitely a lot from human behavior and human driving. On the other side, it's really dangerous because if we copy too much human, we will do the same mistakes. So in my view, the purpose of automation is really to replace the human, not to replicate it, and we need to have superhuman capabilities in all sense for perception, for motion planning, decision making, and for control. And this requires really multimodal, multi-channel observation of the environment. So how to do this? We are using radars, LiDARs, ultrasonic sensors, cameras to do distance estimation. The sensors have different strength, different weaknesses. They are working at different conditions. And they can be used in a very nice way to work together and to strengthen each other. so as to increase the overall confidence of the distance estimation or that of the object existence hypothesis. Radars, there is a lot of radar. Flash radars has gone. FMCW radars, frequency modulated continuous wave radars are are in use widely, and we are just looking for the imaging radars to come. An FMCW radar emits a modulated sinusoidal wave, so increasing in frequency from periodically, and it receives the back-bounced signal, and it compares the frequency of the emitted and the backscattered electromagnetic signal, and from the frequency difference, from the time delay, and from the shape of these two signals, with simple trigonometric identities, one can calculate the distance and the speed of the object from which the electromagnetic wave backscattered. This is very good because this distance measurement is based on physical principles, laws of physics. It's comes with very high confidence. However, it has limitations. For example, the angular resolution of a radar is not so good. It's around 1 degree, maybe just a bit below 1 degree. The elevation measurement is very basic currently. It's improving a lot, but it's not yet there. And the close ranges, like below 1 meter distances, are difficult to measure because the backscattered wave frequency is so much close to the emitted wave frequency that the differentiation between the two is problematic. But it's a very secure way of measuring distances. However, there are materials which are not metal, not water, which are absorbing this kind of wavelength, 77, 79 gigahertz or 24 gigahertz. So there are no backscattered wave. And in that case, a radar cannot decide whether something is there, just the wave have been absorbed, or there is nothing there. What about LiDARs? As one of the famous market analysts, Peter Kromer, said, LiDAR market is a battlefield where startups are disrupting other startups. What does it mean? This LiDAR and laser technology is so much changing, so much evolving, that every month there is a news, there is another technology popping up on the market with great promises. There is more than 50 different companies in the world trying to produce or already producing LiDARs. There are flash LiDARs, there are TOF LiDARs, FMCW LiDARs, and they are very nicely complementing each other. They have different properties. Let's see how we can use LiDARs for distance measurement. A simple TOF LiDAR, which means time of flight, measures the time an emitted laser pulse returns back to the source and divide the times with the speed of light and by 2, and then it gets the distance of the object from which the light backscattered. It's really simple. It's really simple to implement. It's cheap. It works. However, there are problems with multiple scattering. There can be problem at snow, at rain, at fog. And it's reliable. The precision is really high. Its reliability and robustness is not so good. How about flash LiDARs? Maybe the terminology is not that clear. Here with flash, I mean that there is a flash, a source of global illumination, a laser source, and there is a camera on the receiver side, and both is exposed. Exposition happens at the same time. And the camera collects all the light emitted by the laser source. So we get a measurement which reflects where you can determine the reflectivity of the surface from which the light backscatters. So if I have a black car in front of me and a white car in front of me, of course, much more light will scatter back from the white car than from the black car. Okay, but how we can measure the distance? No, let's do the same exercise. Let's flash the LiDAR. Let's make an exposition with the camera, but with a bit of time delay, which results that the light which scattered back from objects which are too close to the camera will arrive back before the camera exposition starts. So they don't get integrated. That information is lost. Only the light which scattered back from far enough objects get integrated by the camera. And as a result, the integrated intensity of the light by the camera will be linearly proportional to the distance of the object. And using the previous measurements, which we took as a reference, and this current measurement with the time-shifted exposition of LiDAR and camera, we can easily calculate the distances of objects. Why this is useful? This is very useful because you have the resolution on the receiver side. So again, you have a global illumination, you have a camera, a high-resolution camera, like 2,000 times 1,000 pixels, and you have the resolution on the receiver side. It's very accurate in angular terms. It's also accurate in distance measurement. However, the distance is limited. If you think about how much energy you would need to illuminate an object 100 meters away, globally illuminate, I mean, not just scan-like, that really limits the usability of this technology for long-range sensing. This is a very good proximity sensor, very good use in I don't know, movie industry and other industries. Yeah, this is what I just thought. Sorry, this is the same slide. Ultrasonic is one of the simplest and maybe one of the longest in use. Ultrasonic, a sensor emits sound waves. So those are not electromagnetic waves, but sound waves. They are propagating through the air, backscattering from surfaces. And using the time of flight principle, the sensor can determine the distance of the closest object. This is really, really simple. Current sensors practically has no angular resolution. They have a field of view. And if there is an object somewhere in that field of view, anywhere, it will measure the distance of that object. They are extremely cheap, so you can have 24 ultrasonic sensors around your car. It will give you a quite reliable proximity sensing at low speeds. However, at high speeds, for example, at highway, their reliability is highly decreasing. Also, a typical range of an ultrasonic sensor ranges between 6 to 12 meters, really depending on the energy and on the environmental conditions. There are new developments targeting 3D ultrasonic sensors. So the sensor will not just return with a scalar value of the closest object distance, but it will give you a 3D pattern of objects. This kind of technology is still in development. But let's see what we can do with cameras. And maybe here I stop for a moment. Since we have seen that LiDAR is so accurate, LiDAR has 2 centimeters of accuracy, why bother with other technologies? And the reason for this is really safety and diversity and redundancy. So what automotive industry prefers is really guarantees over features. It's better to have a modest feature with high guarantees than some fancy feature with lower confidence. And distance measurement should come at the highest confidence. And for that, a diverse sensor solution is a must. One cannot do in a different way. So cameras are a very nice way to complementing the LiDARs and the radars, and the other way around is also true. So I think, as known by everybody, a classical stereo setup is one of the easiest way to measure distance. You have 2 cameras separated by the base distance. And you identify the same object on the 2 camera image. In this case, this is a running man. And if you overlay that 2 pictures onto each other, then there will be a horizontal shift between the 2 images. And the amount of this horizontal shift is called the disparity. And the value of the disparity, the horizontal separation of the 2 images, is inversely proportional to the distance of the object. You can try this by closing your left eye and then closing by right eye. Looking at the same object, you will see that object moves a bit. And this principle is used in stereo measurement. It's really very nice because it uses the fact that the space is 3-dimensional. So it's kind of based on geometry and the laws of physics. But there is one weak point of stereo measurement. This is the feature matching. In order to calculate the disparity, one has to identify the same feature on the two images, and that could be prone to errors in non-ideal conditions. So if there are no features like featureless regions, a wall, a white wall, or if there is heavy rain, then it can be problematic to identify the same feature on the two images at high accuracy. We can do distance estimation with AI using mono camera, single camera, or stereo camera solutions. Let's see how it works. As I mentioned, in the stereo case, the feature matching is a problematic, and AI, artificial intelligence, is really powerful to enhance our capability in feature matching. So we can do the same exercise, having two cameras, but we do the feature matching part with AI, with a trained AI agent, and that really enhances the performance of the system. If you don't have a stereo camera, in many use cases, in many ADAS use cases, you only have a mono camera. You can still do distance estimation through learning, through database methods. Also, this can be done in a supervised and also in an unsupervised way. I show you this video. This video is taken in Budapest, Hungary, on a sunny day. You see a forward-facing camera. We're doing pixel by semantic segmentation and depth estimation. On the upper image, you see the categories. The people are blue, the cars are green, and the sky is red, just the other way around, so the people are red. And on the lower row, you see the AI-based monocamera single-frame distance estimation. What does it mean? The AI gets a picture, it processes it, and just like you, as you are looking at a photo, which is flat, and you cannot use your stereo eye, your stereo vision, but you are still able to estimate the distances of the objects in the photograph. An AI agent can do the same. It can estimate the distances. And you see that it was a bit blurry. It was not that precise, but it was very robust. So what I'm saying is not one is better than the other, but they are very nicely complementing each other. A classical stereo solution is more accurate. It's sharp. The contours are nice, but it can be unstable, especially it's prone to calibration errors. An AI-based solution is not so accurate currently, but it's very robust, and putting these two together, these two features, creates a system which better than any of the single one. Okay, what else we can do? We can estimate distance of objects if we know their size. What does it mean? By now, as of today, classifying vehicles by AI is really easy. So I can classify a Ford Mondeo produced in 2006. And having a database, I exactly know the size of that vehicle. If I know the size of the vehicle, the physical size, and I measure its screen space size, then using simple triangulation, I can really determine the distance of the vehicle. Why this is, it's extremely precise, and it also works at very long distances. So I can see a car 300 meters and determine its distance at high precision if I know its physical size. Of course, it requires a very high precision classification capability, but this is the only error source of this method. Practically, it works as a stereo camera, having a virtual baseline of 2.5 meters, equivalent to the width of the car or the length of the car. But what if I don't know the size of the vehicle in advance? I can still do something. For example, if there is a vehicle in front of me, a truck, I can measure its distance and its size, for example, using my stereo cameras. As the vehicle goes away and it gets out from the range of my stereo vision, I can still remember its physical size and use the previous method to estimate its distance. So if I measure the vehicle which are close by, I can still follow them to very high distances since I remember their size. One can do this with vehicles, or you can do this with the road. If you can measure the road width around the car, the width of the lane, and you assume, or you know from map information, that the width of the lane is constant in the next 5 kilometers, then you can identify objects which are very far away, and you can calculate the ratio of the far objects and that of the visible lane width, and using, again, simple triangulation proportion, you can calculate the distance of the object. I intentionally don't go into details. I just want to outline the principles behind this distance measurement method, since there is no really time to discuss them in details. Again, one of the simplest methods, what if I only have one camera? How can I measure the distance? It's really simple. Our roads are quite flat in principle at this scale. So a vehicle is always driving on a kind of flat road, or if it is not flat, we can still estimate the surface of the road, how it evolves. And if I know, but let's stick with a simple example, let's assume that the road is flat, so it's a big plane. On the screen of my camera, I can identify the touching point, the contact point of the vehicle in front of me on the ground. If I identify this touching point on the screen, on my image, then again, since I know the focal length of my camera, I know the height of the camera mounted on the ego vehicle. Using simple triangulation, I can calculate the distance of the object. This is very robust, again, very precise, since this method corresponds to a stereo vision, having a virtual baseline of 1.62 meters, corresponds to the camera height. However, it uses assumptions. It uses the assumptions that the road is flat, or its uncertainty is the road surface estimation precision. A very interesting one, another one, is how to measure distance, or more precisely, TTC, time to collision, using scale change. In this method, I observe a vehicle in front of me, and I measure its scale change, whether it is shrinking or enlarging. And I take 2 pictures, I measure the time between the 2 pictures, I determine the size of the size increase, the scale change of the object. And using delta t and delta s, one can directly calculate the time to collision. What does it mean? I don't know exactly how far that object is. I don't know whether this is 100 meters or 200 meters away, but I know that this will hit me in 2 seconds or 2.5 seconds. So this is not good as it is for exact distance measurement, but this is good, for example, to cruise control, to following a heading car, and to adjust the speed of the ego vehicle in order to avoid collision. And it does not require any semantics. Scale change can be really easily calculated from optical flow. So this is, again, a very reliable method. SLAM, SFM, I'm not going to go into details. Structure from motion, SFM and SLAM, simultaneous localization and mapping, they are very similar methods. SLAM is using a kind of optimization, so it's not only determining the position of the objects, features, points around the vehicle, but it's also optimizing the ego motion of the camera, the ego motion of the vehicles. This technology has a whole list of literature and a very promising technology. Very precise, one can do very precise localization. However, the robustness and the reliability between different weather conditions or different seasons is still questionable. And it requires quite big map size, data size, to be able to perform localization on it. Still, there are very good use cases to use this one. I have only 2 left and 1.5 minutes, so I try to squeeze that in. What if you have only one camera and you have a heading motorbike in front of you at night? That motorbike has only one light, one point-like light source. When you are approaching the motorbike, there is no motion parallax, which means that the motion is in the line of the objects. So you cannot use SLAM, you cannot use scale change, you cannot use any method because you are just in the same line. The only method you can use is really to measure the intensity of the light. how it works. You measure the intensity, the integrated intensity of the rear lamp of the motorbike in one frame. You integrate it. You fix your exposure time. You wait, let's say, 1 second. You measure again. Since we know that the intensity of the light of a point-like light source decreases as 1 over r, where r is the distance, having 2 measurements and 2 unknown variables, we can determine the distance of the motorbike. This is the only distance measurement method which does not use any assumption. All the other camera-based distance estimation methods are using some assumption. This method has other limitations. It works perfectly in this special case when you have an active light source, there is night, and you can fully integrate all the photons coming from the light source. But in generic conditions, this is, again, difficult to use. The last method is, again, measuring light intensity, but in an active way. So you don't measure the intensity coming from another light source or from ambient light. But it's very good for proximity sensing. Let's imagine that you have a line of light on the side of your vehicle, like that protecting plastic line that is usually there. It can able to emit light. And you also have a point light source on the side of the vehicle. We know that the light intensity of the point light source decreases as 1 over r, while that of the line type of line source decreases like 1 over r, not r squared. You do 2 images with your camera. On the first image, one of the light sources illuminated. On the other image, the other light source is illuminated. You get, again, 2 measurements, 2 equations with 2 different light curves. You can measure the distance of the object from which the light scatters back to your camera. This is, again, a special use case. It's not a generically usable, but it's very good for proximity sensing, for active proximity sensing at high resolution. Currently, high-resolution proximity sensing is missing. There is only one company producing tools or sensors that are good for that. This is the very last slide, so here I compare the results. The main message is not really the numbers, because those are a function of parameters and setup that have been used for the simulations. But the main message here that different kind of distance estimation methods has different characteristics, different dependence on range, on baseline, on light intensity. They are behaving differently in different region of the space. For example, the ones which are a result of 2 exposition dependent quadratically on the distance. Other ones are depending linearly, so on and so forth. But this is a very nice example that one should use this kind of information when designing a system for a specific use case, for specific vehicle speeds and specific object distances. This information can be fused together to reach an even higher level of accuracy and robustness over the designed operation domain. Thank you very much. This is all what I wanted to say.
Gergely, thank you very much. If you have any questions, please make your way to the microphones. There's 2 set up here in the back of the room. I'll start, I guess, with my standard question for everybody in the automotive space. When am I going to get my L4 car that will automatically drive me to work? What are we talking?
You know, they say that predictions are difficult to make, especially for the future. So I'm not trying to attempt to make such a prediction. I would be the happiest if it were happening soon, but it's factor of many.
You're the first refusal to answer, which is probably the smartest response to that question I've gotten all day, actually. That's great. Any questions for Gergely? Okay, great. He will be available if you want a question, you want to have a more private question. He's available to chat with afterwards. Thank you for your presentation. You guys are now hitting a break period.